Hi, I'm Quincy and this is Physics Lab 4, Oscillations. The purpose of this lab is to compare the predicted motion with the observed motion of an oscillating mass attached to a rope. We can demonstrate this system by a spring mass system. Then, we want to plot the energy changes for the predicted motion, which is the kinetic energy, the potential gravitational energy, the potential spring energy, and the total energy, and then put this all into a graph to compare them. I then found that the calculated data and the experimental data were very similar and that the change in total energy was zero, and this is important, which we will discuss later. The two main fundamental principles are Newton's second law and the energy principle. Newton's second law is F net equals delta P over delta T, and then we can get the velocity update and the position update formulas from that, which are Vf equals Vi plus F net over m delta T, and Rf equals Ri plus V average delta T. And then the energy principle is delta E cis equals W surroundings plus Q. And then we have our equations for energies, which kinetic energy is equal to 1/2 mv squared, and potential gravitational energy is equal to mgh, and potential spring energy is equal to 1/2 ks squared. An important physics concept for this problem is spring forces. The tension force from the rope acts as a spring force, so we can use spring potential energy and have nothing in our surroundings, so there's no work or external forces. This is good so we don't have to calculate for a tension force in the surroundings. The system is the mass, the spring, and the earth, and there is nothing in the surroundings. This means that there is no work in the surroundings, and delta E equals W, which equals 0. This means that we can set all of the energies in this problem equal to 0 and then rearrange for the one that we want to know the value of. In this system, we have gravitational and spring potential energy, and we have the kinetic energy of the mass. Here are some important initial conditions to note. We have our constants. G, which is the gravitational constant, is equal to 9.8. K, which is the spring constant, is equal to 6.83. L0, which is the relaxed length of the spring, is equal to 0.123. The mass of the ball is equal to 0.402. The ball's initial position is equal to negative 0.109, negative 0.6340, and then the initial velocity of the ball is 0. Here's my video and tracker. You can see on the right that the graph makes a sinusoidal curve. Here is my coding. In these lines, I updated the force of gravity, the spring force, the net force, the velocity, and the position through each iteration. We also had to update the spring's position independently so that we could update the spring's force. Then, we had to calculate the energy changes for the kinetic energy, the gravitational potential energy, and the spring potential energy, and then the total energy remained at 0 throughout this problem. Here's my energy graph comparing all of the energies in this problem. We can see that the kinetic energy is represented by the blue line, the gravitational potential energy is represented by the red line, the spring potential energy is represented by the green line, and the total energy is represented by the orange line. You can see how each energy works together in the oscillating system. We can also see how the potential energies change greatly compared with the kinetic energy, but at any given point they add to the total energy represented by the orange line that stays consistent the whole time because energy is conserved and the total energy is equal to 0. The top graph compares the x values of the observed and predicted models, and the bottom graph compares the y values of the observed and predicted models. You can see both graphs are very similar, but the top graph is more similar than the second. We can see this because the red and blue lines in the first graph comparing x positions are almost identical, whereas the second graph comparing the y positions are also very similar, but at the crests and troughs they vary slightly. Possible sources of error are not accounting for other forces such as drag and not accounting for other forms of energy such as thermal energy. We said that there was 0 work done in the surroundings, but we could have not accounted for certain forces. We could have also made an error in the center of mass placement and tracker. For your model system, is the energy principle satisfied? Yes, the energy graph in the previous slide shows that the total energy is equal to 0, as seen by the line representing energy along the x-axis for the whole graph, so energy is conserved throughout the problem. Thank you.